On the morning of February 15, 2013, the city of Chelyabinsk in southern Russia was settling into a normal winter day. Temperatures were well below freezing, the sky was clear, and people were commuting to work, sitting in traffic, or already inside schools and offices. Nothing about the calm atmosphere suggested that Earth was about to be struck by the most powerful space impact event in more than a century. Unknown to scientists and astronomers around the world, a small asteroid was already racing toward the planet at extraordinary speed. Just after 9:20 in the morning local time, the sky suddenly erupted in light. A brilliant fireball tore across the atmosphere, so bright that it briefly outshone the sun itself. The flash was intense enough to cast sharp moving shadows across buildings, streets, and snow-covered ground. Many eyewitnesses later said they instinctively turned away or shielded their eyes, believing for a split second that a massive explosion or even a nuclear detonation had occurred. Some people reported feeling a brief sensation of heat as the object passed overhead, despite it being many miles above the surface. So what made this moment especially unique was how well it was documented. Dash cameras, commonly used in Russian vehicles for insurance purposes, captured the event from dozens of angles. These recordings show a small bright point streaking across the sky, rapidly growing into a blinding white flare, followed by a long, twisting smoke trail that lingered in the cold air. For nearly 2 minutes after the flash, there was an eerie silence. The meteor had already exploded high in the atmosphere, but the sound had not yet arrived. During this pause, many people stepped closer to windows or went outside to look at the strange cloud stretching across the sky. That decision would prove dangerous. When the shockwave finally reached the ground, it struck with tremendous force. The pressure wave shattered windows, cracked walls, and slammed doors open across a wide area. The blast was strong enough to be later compared to a magnitude 4.2 earthquake, even though no fault had moved beneath the city. This initial moment marked the true beginning of the Chelyabinsk disaster. The asteroid itself never touched the ground, but in just a few seconds, it transformed an ordinary winter morning into chaos. What followed would leave thousands injured, entire neighborhoods damaged, and scientists around the world scrambling to understand just how large and powerful this unexpected visitor from space had been. When the delayed shockwave finally swept across Chelyabinsk and the surrounding region, its impact was immediate and widespread. The pressure wave traveled outward for hundreds of miles, striking cities and towns across 6 different administrative districts. Buildings shook violently, alarms sounded, and glass burst inward with explosive force. Unlike an earthquake, which ripples up from the ground, this blast came from above, catching people completely off guard and giving them no chance to brace for impact. The most severe damage was caused not by collapsing structures, but by shattered windows. Thousands of panes of glass failed at once, sending razor-sharp fragments flying into homes, classrooms, offices, and factories. More than 7,000 buildings were damaged, including apartment blocks, schools, hospitals, and industrial facilities. In some areas, entire building facades were stripped of glass. At a large zinc processing plant on the outskirts of the city, a massive section of the roof collapsed under the force of the blast, narrowly missing workers inside. Hospitals quickly began filling with injured residents. Nearly 1,500 people sought medical attention in the hours that followed, most suffering from cuts, bruises, concussions, and eye injuries caused by flying debris. Children were especially affected, as many had been standing near windows in schools after seeing the bright flash in the sky. Despite the scale of the event, no fatalities were reported, a fact largely attributed to the high altitude of the explosion and the structure of modern buildings absorbing much of the force. The freezing winter conditions made the situation even more dangerous, with outdoor temperatures hovering well below zero. Tens of thousands of apartments were suddenly exposed to the cold after their windows were destroyed. Emergency crews and volunteers worked around the clock to board up broken openings with plastic sheets, plywood, and cardboard. In total, more than 100,000 residents were left dealing with damaged homes in sub-zero weather. As local authorities assessed the destruction, a larger realization began to take hold. This was not a conventional disaster. No storm had been forecast, no seismic warnings had been issued, and no sirens had sounded beforehand. The damage had come from space, delivered without warning, and it raised a critical question that scientists and governments would soon begin asking in earnest. If an object this small could cause this much destruction, just how large was the Chelyabinsk meteor that triggered it all? With the immediate chaos under control, scientists turned their focus skyward, beginning a detailed investigation to understand exactly what had struck Earth. The Chelyabinsk event quickly became one of the most thoroughly studied cosmic impacts in human history, thanks to an unprecedented amount of accidental data. Dash cameras, security systems, traffic cameras, and even handheld phones had recorded the fireball from dozens of angles, giving researchers a rare opportunity to reconstruct the event second by second. By analyzing these videos frame by frame, scientists were able to calculate the meteor's speed, angle, and breakup sequence. The object entered Earth's atmosphere traveling at roughly 19 kilometers per second, moving faster than any rifle bullet and carrying an enormous amount of kinetic energy. Its trajectory was shallow, skimming through the upper atmosphere rather than plunging straight down, which allowed it to travel hundreds of kilometers before finally disintegrating. Using global infrasound sensors designed to detect nuclear tests, researchers measured the energy released during the explosion. These stations, spread across the planet, recorded a powerful low-frequency pressure wave that circled Earth multiple times. From this data, scientists determined that the airburst released energy equivalent to several hundred kilotons of TNT, making it dozens of times more powerful than the atomic bomb used in World War II. Yet unlike a nuclear detonation, the energy was spread over a wide area, reducing the likelihood of total structural collapse. From these combined measurements, the true size of the object began to emerge. The meteor was estimated to be between 17 and 20 meters in diameter, roughly comparable to a multi-story building. Its mass was calculated at around 10,000 metric tons, composed primarily of ordinary chondrite material, one of the most common types of stony asteroid found in the solar system. This classification helped scientists understand how and why it fragmented so violently under atmospheric pressure. As fragments rained down, a search began across the snowy landscape south of Chelyabinsk. Small blackened stones were soon discovered embedded in ice and frozen soil, each bearing the unmistakable fusion crust formed during atmospheric entry. The largest surviving piece was later recovered from the bottom of a frozen lake, confirming that while the atmosphere absorbed most of the meteor's energy, it had not completely destroyed the intruder. Instead, Earth had captured physical proof of the event, offering scientists a direct sample of the object that had caused such widespread disruption and setting the stage for a much larger conversation about planetary vulnerability. As researchers pieced together what had happened over Chelyabinsk, one unsettling question dominated the discussion. Why had no one seen it coming? This was not a failure of technology in the usual sense, but a limitation of where and how humanity watches the sky. The meteor approached Earth from the direction of the sun, a region that ground-based telescopes cannot safely observe. Against the overwhelming glare of daylight, the object was effectively invisible until it was already tearing through the atmosphere. This realization exposed a dangerous gap in planetary monitoring. At the time, most asteroid detection efforts were focused on identifying massive extinction-level objects, the kind capable of wiping out entire regions or even civilizations. Smaller asteroids, those tens of meters wide, were considered a lower priority because they were not expected to cause widespread devastation. Chelyabinsk proved that assumption wrong. While the meteor did not leave a crater or level the city, it injured more than 1,000 people and caused extensive damage across a densely populated area. The event immediately drew comparisons to the Tunguska explosion of 1908, another atmospheric airburst that flattened a vast forest in Siberia. The crucial difference was location. Tunguska occurred over a remote wilderness, while Chelyabinsk unfolded over a modern city filled with glass, concrete, and people. For the first time, scientists and emergency planners had real-world data showing what a mid-sized asteroid could do to an urban environment. In the months that followed, space agencies and governments reassessed their approach to near-Earth objects. Detection programs were expanded, and new emphasis was placed on finding smaller asteroids that could still pose a serious threat. International cooperation increased, with data sharing between observatories becoming faster and more coordinated. The idea that asteroid impacts were rare, abstract events belonging to deep time was replaced by a more urgent understanding that they are an ongoing natural hazard. Chelyabinsk also reshaped public awareness. Unlike ancient impacts known only through geology, this disaster was witnessed in real time by millions through video footage shared across the world. The sudden flash, the delayed shockwave, and the shattered windows made the danger feel immediate and personal. By revealing how vulnerable even a modern city could be, the Chelyabinsk meteor transformed planetary defense from a niche scientific concern into a global conversation about preparedness, setting the stage for the final lessons that would emerge from this extraordinary event. In the years after the Chelyabinsk Meteor, scientists continued to study the physical evidence it left behind to better understand how such objects behave during atmospheric entry. Fragments recovered from the surrounding region revealed that the meteor was a stony chondrite, one of the most common types of space rock to strike Earth. Laboratory analysis showed signs of extreme pressure and heat, confirming that the object fractured violently rather than surviving as a single mass. These findings helped refine models that predict how similar asteroids might break apart in the future. The event also influenced how risk from space is communicated to the public. Chelyabinsk demonstrated that even without an impact crater, an airburst can cause widespread injuries and infrastructure damage. Emergency planners began incorporating asteroid airbursts into disaster response scenarios, alongside earthquakes, severe storms, and industrial accidents. Public education efforts increasingly emphasize simple protective actions, such as staying away from windows after a bright flash in the sky, lessons directly informed by what unfolded over the city. On a global scale, Chelyabinsk became a benchmark for planetary defense planning. Space agencies used the data to justify new survey missions designed to detect near-Earth objects earlier and from vantage points that can observe closer to the sun. These efforts aim to provide days, weeks, or even years of warning for future threats, transforming surprise events into manageable risks. The meteor's relatively modest size underscored a critical truth: danger from space does not require a world-ending asteroid to have serious consequences. More than a decade later, Chelyabinsk remains the most well-documented asteroid airburst in human history. It stands as a rare moment when a cosmic event intersected directly with everyday life in the modern world. Dashcams, security cameras, and satellite sensors captured a natural phenomenon that once would have passed into legend, turning it instead into a scientific case study. Ultimately, the Chelyabinsk meteor answered the question at the heart of this story. It was not massive enough to end civilizations, but it was large enough to injure thousands and shock the world. Its legacy is a clearer understanding of Earth's place in a dynamic solar system, and a reminder that space hazards are not just relics of the past, but real forces that continue to shape our present and future.